This problem is having us find the first two natural frequencies of a fixed free beam in transverse oscillation. We are trying to find what we will call omega 1 and omega 2 using the finite element analysis technique. Now this problem we did already solve analytically in the previous section because by the boundary conditions being homogeneous, by having a constant cross-section and a constant material, we can use the simplified PDE and find the eigenvalues or the natural frequencies of that system. So we will have a correct answer to compare the finite element results that we get, and we're going to be able to see do our results converge and do they converge to the correct value. As we get to more complicated problems, we are only going to be able to really determine do they converge, and we're going to need some other verification or validation of the numbers we're getting. Are they at least reasonable for the beam that we're analyzing? So since we know from the previous FEA techniques that we did with the axial beams that we are going to need to show convergence, right away we're going to jump in this problem to doing this problem over and over again with a finer and finer mesh and seeing how the omega 1 and the omega 2 are going to converge. So in the meshing or in the modeling step, I'll just draw kind of a small scale generic model that we're going to be working with, and then we're going to scale it up in the code. So I'm going to look at, just as an example, what if we modeled this using 3 elements? So I have elements left to right. I'll call it 1, 2, and 3. And then there's a node on the left and the right of each of these elements. And then we see that 2 of these nodes are going to be shared. Now the difference we're seeing here with the transverse oscillations versus the axial oscillations is that each node is actually going to have 2 degrees of freedom with it. So I'll define them down here. We're going to have W1, which is going to be the position of node 1 vertically. So W1 positive would be that node going up, and W1 negative would be that node going down. But also at this node, we're going to have a second degree of freedom, W2, which is going to be the angle of that node. Then we can go on to that second node between 1 and 2, and that will have a W3 and a W4. And I'm defining these all the same way, positive up for the positions and counterclockwise positive for these angles. So we have a 5 and a 6. And at the end, when we only have 3 elements, we're going to have W7 and W8. So always with the technique we're using with the shape function and how we're defining our nodes and our degrees of freedom for these transverse problems, we see that the odd numbered degrees of freedom always are determining positions, vertical positions or displacements, and the even numbered degrees of freedom are always defining the slopes or the angles at each of those nodes. So in this case, with only these 3 elements, and each one is going to be L over 3 long, and then they'll get smaller as we add more elements there. This would be that first model that we use. As we add more elements, we're going to be adding more degrees of freedom because we're adding more nodes, and each element is going to get smaller. In this problem, every element is going to have the same cross-sectional area. Every element will have the same area moment of inertia, Young's modulus and density. The material is constant, the cross-section is constant. So let's see how we can first get our local stiffness and mass matrices for our elements. Again, in the picture there's only 3, but we're going to be doing it for any number of elements we want. Then how we take those local matrices and create our global matrix from there. But first, to help us out, we're going to use the mapping again. For this small scale one, I just want to keep track for every element what are going to be the nodes it's connected to. So in this one, I have elements 1, 2, and 3. So I want what is the position on its left, what is the angle on the left side of it, the position on the right, and the angle on the right. And we're going to see it's the same pattern for all of them. So for example, for element 1, the position on the left is defined as degree of freedom 1, then 2, 3, and 4. And going on to element 2, it's going to be 3 and 4, 5 and 6, then 5 and 6, 7 and 8. And if we add more elements, we'll see that that pattern would continue. But again, making this map list here, or the map, is going to help us because then we know when we make the local mass and stiffness matrices what rows and columns it's going to be slotted into in the global mass and stiffness matrices. In MATLAB, this is going to be, again, for any number of nodes that we want to look at. So I'll be running this one from using only 2 elements to 300 elements so that we can track that convergence as we add more elements and add more nodes to our structure. And I'm only going to keep track of the first 2, the lowest 2 natural frequencies for this exercise, and we'll be able to compare them to the results we got analytically, which we know are correct. And I'll put in these parameters here. So let me just get this started. All right, so this outer loop, like we saw in the axial problems, is going to iterate adding more nodes and rerunning the finite element code each time. So let's just start by looking at the example we had on the paper. So this would actually be jj equals 2. So we can just see what this would look like in the small scale. Right, so if we look at initializing the k and the m, we have k and m are 8 by 8, and this makes sense because as we just saw in the drawing, we have 8 degrees of freedom when we have 3 elements. So initially m and k are going to be the number of degrees of freedom by the number of degrees of freedom. Then we can create this map list, and that's just what I wrote before. So we see here for element 1, 1, 2, 3, 4, element 2, 3, 4, 5, 6, and element 3, 5, 6, 7, 8. And this map list will grow and always be correct no matter how many elements, how many nodes we are looking at. And then little l, the length of each of the elements. Because I'm only going to be using uniform sized elements for this analysis, I can just divide that total length L by the number of elements I'm using. So now I'm going to go element by element and create each element's local stiffness and mass matrices. So here, these are defined the same way they were defined on the slides. So using this particular shape function, these were the stiffness and mass matrices, the local stiffness and mass matrices that we came up with. Again, this particular shape function is good if we are working in materials that are linearly elastic and we're staying below the yield limit, we're staying in that linear elastic region. So even for a different type of material, or if we're going into plastic deformation, in that case we might want to use a different shape function, which is then going to change our local mass and stiffness matrices. But let's say, just for example here, we're looking at the first element. Let's make that element's mass and stiffness matrices. I have to pre-allocate this. Okay, so this is for element 1, we can see it's KE, and we'll be able to see it's ME as well. For transverse bending, where we have no axial load, like we're looking at here, each of these local matrices is going to be 4 by 4. And that's because that each element has 4 nodes attached to it, a position and angle on the left, a position and an angle on the right. So this is for element number 1. And then down here, like we did for the axial problem, I am going to slot this into the appropriate spot in the global K and the global M matrix. So right now K is all zeros, and if I run this, now it's going to be in the correct locations. So columns 1, 2, 3, 4, rows 1, 2, 3, 4 for this first element. And then the same thing for M. Let me go one more iteration here just for example. So I'm making j equals 2. This is then talking about the second element. Because the A, the E, the I, and the rho are all constant, KE and ME is going to be the same for each of the elements, and that they have all the same length. So when I make those, and now let's see how K is going to change with the second element. So I slot that in, and now we see that we have results from that first element and from our second element put together there. And we can go through then this whole iteration and fill in the K and the M matrices. And at the end of this, we are going to have then our global stiffness and mass matrices defined. So let me just do that for completion here. All right, so this is what we get for K, and this is what we get for M when we only have those 3 elements. So now let's go back and see how do we apply our boundary conditions for this problem. When we're working with the finite element approach to solving for the natural frequencies or eventually solving for the motion of this system, we need to impose our boundary conditions. And we're going to do that for these homogeneous boundary conditions by eliminating rows and columns of appropriate degrees of freedom. In this case, where we have a fixed free beam, we want to see where do we know at all times that the position or the deflection is 0, where do we know at all times that the slope is 0. And those are the only boundary conditions we need to enforce with finite element analysis. If we know that the internal bending moment is 0, if we know that the internal shear force is 0, that will not be reflected in the finite element code. So in this case, looking at our small scale model here, we are going to see that W1 is always 0 because the deflection at the wall always is going to be 0. It cannot move up and down. And also we're going to see that W2, the slope at the wall, is always 0. It cannot be a non-zero value. Now, when we did this analytically, we had two other boundary conditions, which would be at the free end, but that was on the internal moment, bending moment, and that was on the internal shear force. So again, nothing in the finite element code needs to be changed for those boundary conditions. So what does this do? This is going to say W1 and W2 are always 0. So that means for the K and the M matrices, we are going to eliminate here the first and the second column and the first and the second row. And if we think at in a larger scale, what's going to happen if I add more elements? How is this generalizable? Well, as I add more elements, if I add an element 4, a 5, a 6, still the way that I'm numbering from left to right, always degree of freedom 1 and degree of freedom 2 are going to be the ones that are eliminated no matter how many elements I have in my system. So as long as it's always the first two rows, first two columns, that is going to be properly enforcing these boundary conditions at the wall. So K and M, I need to eliminate those in order to enforce these boundaries. So that's what I do next, is enforce my two boundary conditions. So I see in 50 and 51, I'm going to take K and I'm only going to keep the third column to the end and the third row to the end, and the same thing with M. So if I run just that, I see down here, my K and my M are now only 6 by 6. So boundary conditions have now been enforced. And finally, then, with these reduced K and M with the boundary conditions enforced, I can find the natural frequencies of the system. So I do that using the eigenvalues of M inverse K, or M backslash K in MATLAB for speed. And I can see what the, in this case, 6 natural frequencies it comes up with are, and sorted. And I'm only going to be keeping the smallest 2 because that's what I'm going to be tracking. And automatically in this code, I am only keeping the smallest 2, but this can be modified if I wanted to track more than that. And then I'm going to save those to this WN list for the natural frequency list, so I can track the convergence as I add more and more elements. But we see here with using only 3 elements, these are the estimates we get for the first 2 natural frequencies. So that's the basics of how this works in the small scale. Now I'm going to run this entire cell because I want to run this as I keep increasing the number of elements. And for this example, I'll run it to 300 elements and see if we have convergence, at least in those first 2 natural frequencies. Right, so it's completely run. So let's look at the convergence of these 2 natural frequencies. So we see that omega 1, the black line, omega 2, the red line, are both flattening out here. Now again, this is an example where we already knew what the first 2 or all the natural frequencies should be because we were able to solve this analytically. And going back to the analytic version of this in the previous section, going through all the steps here with the PDE and then applying boundary conditions and using this matrix and finding its determinant, we saw that the first 4 natural frequencies, again, we only care about the first 2 right now though, but the first 4 were 444 radians per second, 2,781 radians per second. And these were rounded off a little bit because of the ways we were finding those beta values. So these are not, don't have infinite precision. They're not nice and neat like when we were doing the axial problems and we had that nice like n pi c over L calculation. This one's going to be a little bit less precise, but we know that these are the values about that we should be reaching, 444, 2781. And that's why I have in here on this log-log plot. With a little bit more precision though, I'm dividing my first natural frequency as I track it by what I found, 443.6811. I kept a couple more decimal places. And the second natural frequency, again, dividing that by what it should be to some precision, that 2,780 or so. So looking at this convergence plot again, that's why we see here the y-axis, I am dividing each one by what I found analytically. So let's just see what it's taking for reaching convergence. For the omega 1, we see that line gets down flat pretty quickly here. I would say by at most 10 elements, the omega 1 has converged, and it's converged to 1, meaning the natural frequency we're getting from the finite element analysis is matching very, very closely what we got from the analytic, which we are taking to be the correct value. So after only 10 elements, the first one has converged. If we track the red, the omega 2, it's starting a little bit higher than what it should be, but it also, after, let's say here, maybe 15, 20 at the most elements, has also converged to the correct value, or again, the value that matches what we got analytically. So we see in this problem, the finite element analysis has done its job. It's converged, and it's converged to the correct value. If we were really interested in finding more of the natural frequencies, the third, the fourth, etc., well, then we would just probably have to run this a little bit more to make sure that the third, the fourth, the fifth natural frequency have also converged by the time we declare it working correctly. And as a last piece here, let's just look at our wall time. It might not have worked exactly correctly. All right, it didn't do a terrible job. We see that as I track how long it takes to run the code, as I add more nodes to it, or as I add more elements to it, that the total time is increasing, and a quadratic fit does a pretty decent job at estimating that time. So the exact fit is not too important here, but we just want to realize that the cost of adding more precision, adding more accuracy to our natural frequency is it's coming at the cost of taking a little bit longer to run. Now, this is in milliseconds. It runs really quickly here. But if we scale our problem up, make it more complicated, it can start to run more slowly. But we do want to make sure that we are reaching convergence before we start doing any further analysis in our problem. So in the end here, we made our local mass and stiffness matrices. We slotted them into the global. We kept increasing the number of elements we used. And at least as far as the first two natural frequencies go, by the time we reached 200 elements, and before that as well, we converged to the correct solution based on the analytic approach we used in the previous section.